Hello all, this is Mr. Reynolds, and I'm here today to start our look at cosmology. Past few weeks have been in astrophysics, studying stars, looking at what are they made of, how do they work, how do they die, how to classify them, all that type of things. Today and next week, we are shifting gears a little bit. We will not be focusing necessarily on individual stars. Instead, we're going to look at the universe as a whole. We're going to look at all the cosmos around us and understand how is it born, how is it changed, how will it die, how do we know these things, how can we know the age of the universe? It's very, very old. So they're all things we're going to be covering these next 2 weeks. This is a little bit mind-bending. There's some math, but it's not too heavy. But certainly I do want you to pay attention. So today we're going to start with cosmology. We're going to talk, first of all, about some of the early ways we knew that the universe is more than we thought. You see, many years ago, people thought the universe was stable, it is unchanging, it was eternal, and it was infinite. The universe was, it is, it always will be. Most people have some problems with that. If the universe was infinite and the universe was eternal, that means there's an infinite number of stars, and the light from those stars has been traveling for an infinite amount of time. And so when we look into space, we should see an infinite amount of light. Everywhere we look, we should see an infinite amount of light. And that's not what we see. We see blackness. We see some light. We see some stars and galaxies. But for the most part, we see black. So it can't be infinite and eternal. And so what we did is we started looking at the spectrum. Now, we talked about this a little bit last week. We looked at stars, and I'll just draw you a quick little spectrum. Remember, this black body spectrum of a star, we were able to tell the wavelength, right? We have our peak wavelength, and the 2.9 times 10⁻³ over that wavelength is the temperature in Kelvin. But we also talked about a couple of very important defects to this line. There are a couple places where the graph sort of dipped, these absorption lines. Now, these absorption lines were not due to the star itself. These absorption lines occurred because certain elements are in a star. And one very important element that's in every star is hydrogen. And so we're able to identify a couple very particular wavelengths. For example, 656 nanometers. Hydrogen will always absorb some of the light from a star at 656 nanometers. Okay? There's just no doubt. If you look at the sun, you're going to see a dip in the wavelength at 656 nanometers. We sometimes call this the hydrogen alpha line. Now, if we were in school, we'd be doing a neat little assignment where we did some stuff with that, but whatever. But when we looked around and we looked at distant galaxies, we noticed something very strange. We could identify that hydrogen alpha line and all the others, but we'll just focus on hydrogen alpha for now. We could identify where that was in the spectrum. But when we looked at an observation, what we noticed is this. That hydrogen alpha line, we knew it was hydrogen alpha. We can tell the patterns. Let's say that hydrogen alpha is at a wavelength of, 720 nanometers. Now, we assume that the hydrogen in that distant galaxy is the same as the hydrogen here on Earth. And so, why would that wavelength be bigger? And this is where we start talking about this idea of Doppler effect. Remember the Doppler effect. It's when some source is giving off a wave, and that they're even moving towards us or away from us. So imagine that we are here. The star is giving off a wave. It's just visible light, not sound, but that's a wave. In order to get a bigger wavelength, in order to observe a bigger wavelength, that star must be moving away from us. The star, remember, if you're moving away, the frequency goes up, the wavelength goes down. I'm sorry, that's exactly opposite. Too late in the day. Frequency goes down, and the wavelength goes up. Okay? And here's the cool thing that happened. When we looked at all the stars all around us, and all the galaxies all around us, that's key here, they were all moving away from us. Everywhere we look, every direction. Look to the north, look to the south, look to the east, look to the west. All the distant galaxies are moving away from us. that made us wonder why that was. We'll get to why that is. Real quick, I want to talk about redshift. We do have an equation for redshift. The equation is this. Is that we're in D.3, by the way, if you want to look at your data booklet. Z equals delta lambda over lambda naught, which about equals V over C. Let me identify what some of these things are. Z is it's called redshift. If the problem ever asks you what is the redshift, that's what Z is. It's going to be a number, 1 to 3, 4, 5. It could be as high as you want. There is no unit to redshift. Delta lambda is the difference in wavelengths. Lambda naught is the original wavelength. V is what we call the recession velocity. All these things are going away from us, so we call it recession velocity. Recession refers to going away. And C refers to the speed of light. Now, in the IB curriculum, they do give us that sort of wiggly equal sign. Right here is sort of the wiggly sign. That means it's about equal to. For our purposes, we're just going to consider it equal to. So, for example, in this problem, we could do some math. We could say, well, let's see, delta lambda over lambda naught equals Z. We could calculate the redshift. So the difference in the wavelengths here is, that looks like about 64 nanometers. And the original wavelength was 656 nanometers. And when I do this math, 64 divided by 656, and I do it properly by putting a decimal point there, we're going to get about 0.099 for the redshift. Okay, that's a decent redshift. If I wanted to find the recession velocity, I could take that number, I should say 64 nanometers over 656 nanometers is about equal to V over C, and we could solve for the velocity by multiplying by speed of light. The speed of light is 3 times 10 to the 8th. That's in the data booklet, of course. 3 times 10 to the 8th multiplied by all those things. And whoops, let's do the math. I'm using a calculator here and making a complete hash of it. It's almost like I haven't been using calculators a lot lately. So that star is going to be moving away from us at about let's just round it off to 3.0 times 10 to the 7th meters per second. So this galaxy, this observation that we made is moving away from us at 3 times 10 to the 7th meters per second. This is what we call the recession velocity. And everywhere we look, things are moving away from us. That's wild. Why is that? Why could that be? Well, let's have a think here. Let's have this big red thing here. Let's say this is us. Okay? And then I'm going to put a couple galaxies around us. These are different galaxies. Okay. And we can measure a couple distances here. Dump and bump and bump. Okay. Now what's going to happen is, what we decided is, it's not that we smell. Because what's special about us? As far as we can tell in the universe, there's nothing special about the Milky Way. There's nothing special about our galaxy. Okay, I know we like to think that we're really special, but in cosmological terms, we're really not. So we wonder why this is. But what we figured is maybe the universe is expanding. If the universe is expanding, well, all of those... Maybe I should do this. I'm going to copy that. Then we're going to take you. I'm doing some high-tech stuff here, guys. We're going to take you. We're going to expand you out. Okay. And then I'm going to paste. So what you'll notice is, no matter where you look, if you look at the same two stars, let's identify equal stars, here and here, okay? Here and here, here and here. All the stars in all directions are moving away from us. They all moved away in all directions. And what happens is, here's the deal. If we check from any other star, if we model this from any other galaxy at least, the same thing is happening. So not only is everything moving away from us, everything's moving away from everything. Because here's the idea. Came up with this idea called the Big Bang Theory. Let me tell you what the Big Bang Theory is not, first of all. And we're not getting in a religious war about this either. I know sometimes tempers get heated. email me if you have questions. I'll talk to you all about it if you have questions and you want to discuss that aspect of things. But here's what the Big Bang Theory is not. Big Bang Theory is not, hey, in some place in space, there's this really, really tiny thing, and it went and it filled up all of space. It's sort of like if I take a smoke bomb and I let it off in the room, right? That smoke fills up the room. That's not what happened. That's not what happened. If it was, then there would be a spot I could point to in space, and we could say, hey, that's where the Big Bang happened from. That's where all the stars came from. That's where everything came from. Just like I could point in my classroom and say, hey, that's where that smoke must have come from. That smoke bomb right there. But we don't see that. We see every part of space seems just about the same. What happened instead is that we started. Now, again, science is not answering where does this come from, what happened before time zero. We don't know. Scientists, they like to answer that, but we don't have those answers right now. But it's not that all of matter was condensed into a tiny point, but all of space itself was confined in this tiny, tiny little spot. All of space and energy and matter, at that point matter didn't really exist, is basically pure energy. Energy can turn into matter, E equals mc squared, but we'll get into that next year. All of energy and matter is condensed all in one space. And at some point, for some reason, space itself expanded. Space itself got really big really fast. And it is continuing to expand. Space itself started to enlarge. It's not like a smoke bomb in my classroom filling up the room. It's like my room being filled up in this tiny spot, and my room and everything in it expanding. If I go back up here and we look at this image of what's going on with our space here, when I'm enlarging this image, I'm not moving the other stars away. I'm enlarging the actual space itself. And as we look all around us, the only thing that can explain why everything is moving away from us is because space itself is expanding. Now, this is not an excuse. When we're done with this coronavirus thing and you come back 15 pounds heavier, you cannot use the excuse, well, space is expanding, so, it's not really my fault. No, you just need to stop eating ice cream. You see, we have forces holding us together. Certainly, we are not affected by it. In fact, in the Milky Way, we don't see all the stars moving away from us. The Milky Way is held together tight enough where the expansion of space really isn't a thing. This is something that only really happens over very large distances. We only notice it with very distant things, like distant galaxies. Like the nearest galaxy to us is Andromeda. It's actually getting closer to us. But for all intents and purposes, when we look at space, we look at very distant things, the velocity of those very distant things just doesn't really matter. Because once you get farther away, space is expanding more. Let me explain that. Imagine we take a rod and we mark, A, halfway I'll do B, and halfway I'll do C. Okay, there's 3 positions on this. Now what I'm going to do is I'm going to copy this. I'm going to paste it so we have an identical thing. And I'm going to take this object, the second object, and I'm going to expand it until it's roughly twice as large. It's roughly twice as large. And I want to think about what happened. Imagine we're at A. Okay? And we're looking, and we're seeing, let's look at star B. How fast must star B be moving away from us? So, some amount of time happened here. Well, star B traveled this distance B, in a certain time. Star C traveled this distance in the same amount of time. So which object would appear to be moving faster away from us? Turns out the object moving faster away is going to be that object that's farther from us. As we look into space, the farthest, most distant galaxies are the ones moving away from us faster. How do we know? Well, we can test it. We have this fun equation right here, right? The redshift from galaxies very, very far away is a much, much more dramatic value, much bigger redshift farther away. Things closer have a smaller redshift value because it's not the stars and galaxies that are moving, it's space itself that is expanding. We have an equation that deals with this. This is another equation that deals with redshift. That z is still the same redshift. But we have this value called r. Now, r is referred to as the scale of the universe. I can't spell universe. Universe. And there's a -1 here. Oh, I'm messing everything up. This is sort of like the meter stick for the galaxy, for the universe, right? Scale of the universe. The bigger the space has gotten, the bigger the R value has gotten. So let's take that star we saw up here. It has a Z value. Let's just round it off to 0.1. Okay, our Z value is 0.1. So I could ask you this: when the light from that star, from that galaxy, because light takes a long time to get to us. When you see a galaxy that's 10 million light years away, you are seeing light that was produced 10 million light years ago. Just sort of weird to think about. When that light was produced, the universe must have been smaller. By the time it has gotten to us now, the universe has gotten bigger. How many times bigger is the universe now compared to when that light was first produced? I'll say it again. That light was produced a long time ago. It has taken time to get to us. In that time, the universe has expanded. I know the universe has expanded because look, look at this. The wavelength, which was 656, is now 720. The universe has gotten bigger. That's why that wavelength got bigger. So how many times bigger would that be? Well, we can plug this in. I can solve for what is the current scale of the universe, r, in terms of the original. So what I can say is, well, let's see. If I rearrange this, I'm going to say r equals r naught multiplied by z plus 1. So you have to add the 1, multiply by r naught. And pretty simple equation here. The scale of the universe now equals 1.1 r naught, which means the universe now is 1.1 times larger than the original scale of the universe. When I say original scale of the universe, I'm talking about the scale of the universe when that light was first produced. This is pretty wild. The universe is expanding. The farther away things are, the more it's expanded. Now let's take this, I know I'm going long in this video, but let's take this to extreme. Let's imagine it is Big Bang time. Oh, I'm writing with my highlighter. Big Bang. Okay. Let's say this spot right here in the Big Bang, this is where we actually are. Okay, so that little minute part of space, that's actually where we turn out to be right now. That's space. And let's say there was some light produced. See, when the Big Bang first started, all that energy was condensed into a very, very tiny spot. Well, when you condense energy into a tiny little area, boy, that's going to get hot quick. Okay, and so it was glowing. The universe was glowing at that point. It was so hot and crazy and chaotic. It was wild. And let's say, we may be separated by a tiny little distance. Let's just say, 2 centimeters, separated by 2 centimeters. And then the Big Bang happens. Now, I would think normally light is going to travel to us very, very quickly. In 2 centimeters, light takes almost no time at all to travel that 2 centimeters. Okay, that's crazy. Tiny, tiny amount of time. But let's imagine this is happening right at the Big Bang. And at the Big Bang, it was a very dramatic expansion of the universe. So while that light is traveling the speed of light, the space between us expanded so fast that light never got to us. In fact, that light, which started 2 centimeters away from us, has been traveling ever since the dawn of the universe to get to us. That light has been traveling so far to get to us because the space keeps expanding and keeping it away from us. By the time let's say it just now got to us. Originally, that light was visible light, or probably even, maybe even ultraviolet or whatever, some, probably visible light type of light. But now it has been redshifted so much, it's turned into a microwave. And see, this isn't rare. Everywhere we look in space, we see microwaves, seemingly coming from nothing. Everywhere we look in space, we see microwaves all around us. We call this the cosmic microwave background. Everywhere we look, it's pretty consistent. Don't know where it's coming from. Those microwaves, when we look at them, we can't look at them with visible eyes, but we can see them with microwave detectors. Those microwaves are an image of the Big Bang. Those electromagnetic waves that we are receiving are the waves produced during the Big Bang. We can see it all around us. The cosmic microwave background is all around us, and it is the Big Bang happening. By studying distant objects, we are going back in time. Now, this seems sort of weird. It seems sort of wild. One important thing to know about the universe, because the universe all started from one tiny spot, is it is totally fine for people to say Signal Mountain is the center of the universe. Yes, the Big Bang happened right here. It happened in your room. It happened on Signal Point. It happened at the high school. It happened everywhere. Big Bang happened everywhere. And we can see it still happening. It's not happening anymore. It happened billions and billions of years ago. But those waves that were produced during the Big Bang have taken billions and billions of years to get to us. And we can actually see it happen. Wild stuff. This is our first video on cosmology. The next video, we're going to take a quick look at Hubble's law, which we'll sort of pick up with this redshift and distant objects and all this kind of stuff. And then that'll be the chapter. Thank you all for sticking with me. I know this is a mind-bending chapter. Please check out the crash course videos that I'm attaching to this lesson as well. They do a real good job of explaining some of this as well. And please let me know if you have questions, either in the Zoom chat or again, if you obviously religion plays, sometimes religion has an issue with this. And there's, people get sort of upset when talking about the Big Bang Theory and all this and how I'm trying to kill God or something. No. If you have questions about that, please let me know. I'd love to talk with you about that. And, so don't let that be a stumbling block for you as we go through this chapter. Hope you have a great day. Next video coming out very soon. Thank you.